Hello everyone, how are you all? Hope you're all doing well. Welcome to our webinar today that we're going to run on PD data analysis and how to interpret PRPD patterns, phase resolved partial discharge patterns. So with me today we have Thomas White, one of our field engineers, and I'm Brad Monaghan, and we work out of the Brisbane office for EA Technology in Australia. We've got a few people logging in from overseas, and we have a lot from all around Australia today. So we'll get started. We've got a presentation to go through. Everyone will get sent a link later on to the presentation itself and a couple of other links to relevant information. So that's that'll be what will happen after the presentation today.
Well, as we go, you can ask questions, and we do ask people to ask questions as we go along. Whoever isn't speaking will be answering questions as we go, and then we'll have a bit of a question session at the end for any more questions that you have throughout. You'll also be sent just a full summary of all the questions and the answers in an email at the end of it all.
Yep. So to get to the questions, find that there's a little drop-down box that says questions. You can type things in there. Thomas and I see it come up on our screen, and we can answer that in real time. Okay, so this is the second part of a three-part webinar series. Last time we went through applying the most appropriate monitoring techniques and how to collect the condition data. Today we're going to go through data analysis, and then there'll be a third one on what to do with all the information and how to plan some actions around that. So the contents of today, we'll have a quick overview of PD and the techniques that we use, because we have covered that in the last PD webinar and also other webinars that we've run. We've talked a lot about that information. Then we're going to talk about how is a PRPD pattern created, so a phase resolved partial discharge pattern. How does it come about? What is it? The importance of getting a good phase lock when you're collecting data. And then we'll go through data analysis and interpretation of the patterns, and there'll be case studies throughout the presentation. So let's get into it. So a quick overview of PD, or partial discharge. So the easiest way that I think about partial discharge is sparks, tiny little sparks that are jumping across gaps because there is some sort of defect in your high voltage insulation that can't insulate the bolts in anymore. They can't hold the bolts in the way it's meant to because of there's a defect there, there's a crack, there's a split, there's a void, there's something that's too close to something, there's sparks jumping a gap for whatever reason. So if we think about sparks, what does sparks produce? Sparks will produce light because we can see a spark. It's the same as a tiny little lightning bolt. It'll produce heat because it is a tiny little lightning bolt. There'll be a certain amount of heat given off every time a spark occurs. It will produce a smell, and that's because sparks will produce ozone gas. That ozone gas can get trapped inside high voltage chambers and cause further defects and degradation. It will also produce a sound because we can hear a spark, and it will also produce electromagnetic waves. Electromagnetic waves we can't see, but we can use different sensors to find that activity. Okay, so what we're going to talk a lot about today is the UltraTEV Plus 2, which is this instrument right here, which is our main handheld instrument for doing online PD testing. And what it focuses on is sound and electromagnetic waves. So let's talk about it. Okay, the methods to find sound, or to hear the sound given off by sparks or partial discharge activity. If that sound is loud enough, we'll be able to hear it with our own ears. So human beings can hear from 20 hertz up to about 20 kilohertz, depending on how good your ears are. And if the sound is loud enough, you'll be able to hear it. Now, a lot of the time, the sound won't be loud enough for you to hear, and we use other instruments to listen for that sound. And that's where we listen in the ultrasonic range, and that's why it's called, we're listening for ultrasonics. Now, we've got sensors such as this one. This is your airborne flexible probe. There's a picture of that just here, getting used out in the field. We have an ultrasonic dish, which is this one. There's another picture of it getting used there. And we also have a contact probe, which is this one. These are the three ultrasonic sensors that listen for the sound given off by sparks. That's the easiest way to think about it. Okay, they listen in the 40 kilohertz range where human beings can't hear. And then we've got electromagnetics. So whenever a spark occurs, a little spark will jump a gap. A ball of energy in the electromagnetic, in a range of electromagnetic frequencies, will be given off, and that signal will propagate away from its source in all directions. It will travel on things that are conductive. It'll travel through the air, and we can use a range of different sensors to find that electromagnetic energy. The first one we use is the TEV sensor. So at the end of this instrument, there's a sensor there that we hold up against the outside of switchgear, the outside of high voltage cables, to find TEV signals, or transient earth voltage signals. The next sensor we can use is this one. This is called a high frequency current transformer. The old one was called a radio frequency current transformer. They effectively do the same thing. They are looking for electromagnetic signals traveling up and down the screens of cables or through any earth traps or anything like that. And then we also have UHF. We have a UHF sensor, which is this one right here. That's our main one. That's a UHF directional antenna. The old one was called a PD Hawk, and that is also looking for electromagnetic signals. Now the UltraTEV Plus 2, all of those accessories and all of those tests can be ran with this instrument here. This is the box that it comes in. These are the types of activity and data that you can record with it. You can record sounds, you can capture phase plots, you can record cable PD, ultrasonic PD, TEV PD, you can look at waveforms, you can see the speed of the pulses, you can look at histograms, and you can also record UHF data as well. So that is our main instrument, and that's why we talk about it the most. Another instrument that we can use is called a TEV Locator, and that's this one here. What we do with this one is we plug this into this, and then we have two TEV sensors in our hands, and we can figure out what direction TEV signals are coming from. Okay, so they're all the things that we use to detect PD. And then these are the types of PD. So there's three main types. The three main types are, you've got internal void discharge, where you've got PD on the inside of solid insulation, or on the inside of insulation. You've also got surface PD, and that's where you've got defects on the outside of your insulation. You've got corona, where there's a physical sharp point and there's sparks jumping from that sharp point into a gas. And then the other type, which there is a lot of out there, is called contact or floating metalwork type PD, and that's where sparks are jumping a gap because of dissimilar metals or poor HV connections. So let's get into it. So what is a phase resolved partial discharge pattern? So in short, that is a phase resolved partial discharge pattern. You may have seen many of these in lots of documentation in terms of research into what they mean, how they're created, and what different defects create the different patterns. So in short, on the vertical axis here, you have the amplitude of the signal, and on the horizontal axis, we have where those signals are occurring, or where those events are occurring in relation to your sine wave. So here in Australia, we're running a 50 hertz network for the bulk of the network. I have worked on a 40 hertz network, but 50 hertz, and one spin of your generator is 20 milliseconds of time. It gets measured here in degrees. So 360 degrees of a spin of a generator will give you a sine wave. Now, each of these dots occurs over time, and it is the signals given off by PD activity. Whether that signal is a sound, this is why I was explaining everything before. If we are listening to a sound, the instrument knows the amplitude of that sound, and the instrument knows where that event occurred in relation to the sine wave. And it will put a dot on the screen, and over time, a pattern will get created because you have many, many, many dots over time building up a pattern. We'll talk about that soon a bit more. Now, why is a phase resolved partial discharge pattern so important? The reason it's so important is because we put so much weight into our analysis of what's actually going on out in the real world while we're PD testing. So first of all, let's look at the evolution of the instrument. So back 30, 35 years ago, I'm not sure how long ago it was now, this man here called Dr. John Reeves, did a lot of research with EA technology where they figured out that PD was occurring on the inside of equipment. So maybe we can detect the signals from the outside of the equipment. So here is one of the first TEV detectors ever invented. He's holding a capacitive probe up against the outside of the metalwork, and these tiny little TEV signals are appearing on the outside of that metalwork. Now, as I understand it, as our boss Neil tells the story, this one here measured decibel millivolts, and that's all it measured. So when we first started looking for PD in the TEV range, we were looking at decibel millivolts only. And then research occurred over years, technology got a bit better, PA technology invented some more instrumentation, and then they were able to count up the pulse per cycle count. What the pulse per cycle count is how many times per one sine wave of time that PD events are occurring. And then a heap more testing occurred out in the field, correlation got built up between, right, if I've got this decibel level, if I've got this pulse per cycle count, it's most likely going to be internal void PD or surface PD or a contact type issue or just general noise, electromagnetic noise. And that is what was within the UltraTEV Plus 1 instrument. So now, about 5 or 6 years ago, EA technology invented the UltraTEV Plus 2. And what it's able to see is the phase resolve partial discharge pattern. And what that is this pattern here, where my mouse is, showing you what's going on in the field. Now, the phase resolve partial discharge pattern was always there. It's just that we could never detect it. The only way to detect it back in the past was to high pot something with a high pot set and then look at the signals that are being given off by the PD pulses with an oscilloscope or some very smart electronics that was able to plot it on a screen. Now we're able to simply hold one of these up against the switchgear or plug a sensor into it and listen for sound, and we're able to see where events are occurring with reference to the sine wave, analyze that data and figure out what's going on. Now with sound, the way we used to interpret sound with the older instruments was all you had was the decibel microvolt level and then the user's interpretation of that sound. So to them, whether it sounded like PD, a lot of that was heavily weighted on experience of the user and common problems with the switchgear. Now with the UltraTEV Plus 2, we can see the phase resolve partial discharge pattern. We have an algorithm that runs on the inside of the instrument that is constantly telling the user whether it thinks the sound is created by partial discharge or by some sort of noise. Okay, and that algorithm is running all the time and will tell you what's happening. And then you've also got the sound that you can hear in your own ears, and you've also got your own interpretation of the sound as well. So you've got 4 things to figure out what it is, whereas back in the day, you only had the decibels and what you thought. So the phase resolve partial discharge pattern is very important in that because we put a lot of weight on it. So how is one of these patterns created? The pattern is created over time. Okay, so if you look at the sine wave up here on the left, what we have is, just pretend that blue line there is the voltage on your system. So just say you're running a 22 kV system or an 11 kV system. This here would represent that voltage. Okay, and then you have some sort of defect somewhere that's getting broken down because it can't hold the volts anymore. So if we look at this red line will get charged up, or that defect will get charged up, and a certain amount of volts will be inside that defect. It will get to a level and it will discharge, and that discharge will drop the volts back down to somewhere near 0, but because the voltage on your mains is still rising, it will rise up again, and then it'll discharge. And then not much happens, then it rises, discharge, rise, discharge, rise, discharge, over and over and over, and this happens over and over and over every single time the sine wave is occurring. So over time, I'll just change this to a 10. Over time, what's going to occur is, just say we get one PD pulse happen here and another one here. And then the sine wave comes around and we keep getting one there, 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 one there. And we can see that a pattern is being built up over time because discharges are occurring over time. I hope everyone can see that and understand that. Hopefully the little red dots are coming up on your screen, but as you can see, I'll go a bit faster. A pattern will be created. And I sort of think you get the idea. The pattern will get denser and denser as time goes on. So the longer you hold the sensor there, as long as the screen isn't being refreshed, it will just get denser and denser and denser over time because more and more and more events are being recorded.
And all of the phase plots you'll see in the rest of the slides are all a 10-second recording. So they are quite dense, and that's the default of the UltraTEV Plus 2.
Yep. No worries. Now, the importance of phase locking. What does that actually mean? Now, when we are taking a test out in the field with an UltraTEV Plus 2 or with any instrument, doesn't matter, what you want to do is make sure that the instrument is sampling the data at the exact same frequency that your system is running. So your 50 hertz or your 60 hertz network, whatever's running at the time. So as you can imagine, if my instrument is set to 51 hertz and the system is running at 50 hertz, it doesn't actually have to be all that far out, but just as an example, what will occur is all these dots, all these events will come up onto the screen over time. And if it's not sampled at the exact same time, those events over time will start to drift and form a pattern that does not look like PD. Now, if we're able to lock onto the system frequency, we will find that we will be sampling at the exact same rate that the sparks are occurring. And over that 10-second recording, our phase plot will look good. This is going to give us the best data that we can grab, and that will help us make the best decisions on that data because we can analyze the phase plots off site. You can analyze them while you're there in real time and figure out what's going on. So it's all got to do with your sample rate. Okay, so and just this one here, this is the exact same test in the exact same location where there was a real PD source. It's just this one here was not phase locked, and this one here was locked exactly onto the system frequency at the time of record. So you can see how if we put this into a report or sent that off to other people to help analyze, this here just looks like general noise to me, and this here looks like single phase internal void PD solid to insulation. Thomas will go through a bit more on that, how we figure that out.
Just had a question, just saying the graph numbers, just do you want to explain decibels and the degrees?
Okay, so we just had a question come through. On the left-hand, on the vertical axis, we've got the decibel level or the amplitude of whatever sensor you're using. So when we're doing a TEV recording, it will show you a decibel level from 0 all the way through to 60. If you're doing an ultrasonic, it'll be from -7 up to 70. If you're using the HFCT, which is one of these ones, it'll be measured in picocoulombs and it will just be the scale. So the easiest way to think of it is the amplitude is on the left. So the higher these dots are on the graph, the more energy are in the dots or in the events. And then on the bottom here, we have time. So this is one spin of your generator, which goes from 0, 90, 180, 270, 360 degrees. Okay, so it's not measured in time as in 20 milliseconds, but it could be if you wanted it to be. You just have to convert it to that. Hopefully that answers that question. Now, how do we get a phase lock? Currently, there are 3 options within the UltraTEV Plus 2 to get a good phase lock. The first option and the default option is it will look at the lights that are in the room through a little sensor that's at the top of the instrument. So that's a photovoltaic sensor. And what it does is if your light bulbs will be flickering at 50 hertz or 60 hertz, certain light bulbs, this won't work because you've got LEDs or things that are running at different frequencies. But if you've got a light that flickers at 50 or 60 hertz and you've got a line of sight between that sensor and the lights, it will lock onto the lights. Okay, if that's not working, you can change your setting to the E-field mode. And what the instrument is doing is there's a little sensor in the back of this, and it is hunting for the electric field that's in the air. Okay, so this works really well when you're in an outdoor yard and you've got quite a high voltage and there's a lot of electric field surrounding you. If you can't get it to lock on because you're inside and your voltage is a bit low, what you can do is get a 240 volt lead or a low voltage lead, plug it into your wall, run that over and run your extension lead to the instrument and hold it at the back of the instrument. and I find that gives me a really good phase lock while I'm out in the field. Okay, and then sometimes you don't have a 240 volt outlet near you and you have to do manual. So what you can do is you can manually speed up or slow down the instrument to lock onto the phase. Now in the future, we're going to release another accessory for the UltraTEV Plus 2 where we can remotely grab the phase lock, or I should say the phase reference. So what we'll have is a gadget that you can plug into a wall. This is how I understand it's going to work. It may look a little bit different to what I say, so don't take this as gospel. But we want to plug something into the wall, and it will generate a 50 hertz reference, and it will be picked up through the air by this, or through a Rogowski coil, or through a Rogowski coil. So we should be able to do that. Okay, so that's the introduction. That's why it's important, and that's how it's all going to be put together. I'll hand over to Thomas now to talk about data analysis, and he's going to go through some case studies.
And I'm going to move closer because I just got that in a message that you couldn't hear me.
I couldn't hear me?
No, couldn't hear me. Okay. So we're going to start going through some data analysis and then some real world examples of what we have actually found. But before we get there, the data analysis has a few tricks that we use. And the first one is, what type of PD issues will be detectable by what sensors? And what you can see on the screen now isn't actually gospel. This is a general rule of thumb that we would use for, I'd say, around 11 kV switchgear. And what we go by is the fact that internal void type discharge can be picked up by TEV, HFCT, and UHF testing. UHF testing is more for the outdoor yards when you're not sealed within a metal chamber, but it can still pick up those types of problems. Surface type PD and corona, your main testing source is the ultrasonic, and then contact type and floating metalwork sources can be seen on nearly all of our tests, just due to the nature of them. So when you are analysing these phase plots and these signals, one of the best ways of determining what the original source of the signals could be, is it surface type tracking or is it internal void, what type of maintenance works you need to do, is think about the type of test that has been done and if it's most likely to fall within those categories of defect. The other really interesting thing about PD and the phase plots in general is that every phase plot will end up being relatively unique. Whilst they do follow certain patterns and certain trends, you'll find that every different shape of void, where it's located within the insulation, they will all give you a slightly unique phase plot. So you never should really see the same thing twice, and you'll see that in some of the examples we're going to run through. The same goes for your surface tracking type sources and coronas. Whilst they follow set patterns, you are very rarely going to see the exact same phase plot multiple times. But we have seen very similar plots appear on when you've got a common defect in certain types of switchgear. So these are our electromagnetic or TEV phase plots. So these are some examples of what you will run into in the real world, and they all follow some telltale signs. And that is clusters of activity with 180-degree separation on the sine wave. So your most classic one is this here, the internal void on a single phase. So when we see this type of phase plot, and it's got a good phase lock and we're happy with it, seeing something like this is a telltale sign that PD is present. So when you hear us talk, and if you are with us on site or if you do a training with us, we'll talk about the telltale signs of an internal void is two clusters with a wave type effect. And what we're talking about this is this wave type effect that we're seeing in these clusters. We then also talk about a strong leading edge. And that's when you tend to notice the density on this leading edge here on the left is a lot denser. And in some of our examples, you'll see the textbook example of that where it's got a really strong leading edge going up into a wave. And that is your cliche type internal void discharge. You've then got things like oil and PD inside oil within a transformer. Whilst it still follows that two clusters of activity with 180-degree separation, the nature of the cluster itself is quite differently. Compared to being a wave, you seem to have these clouds that are densest in the middle and emanate out from a spot. You've then got your contact type or floating metalwork signals, which follow a very different pattern. They are still 180-degree separated clusters, but they are long, flat bars of activity. And these type of signals you'll see a lot more in the outdoor yards than anywhere else, and it's very identifiable. The third type, and I think we just got a question about this as well, is what will it look like when you have multiple phases of activity involved? So whereas all of these are a single, two clusters of activity 180 apart, representing a single phase of activity, down here on the right, you have three clusters of activity all separated across all three phases. So this cluster here, its representative cluster would be this here, 180 degrees apart, and that would be activity on one phase. You'd then have activity on a second and third phase here, with the separation of 60 or 120 degrees between all the phases. So once you start to get activity across multiple phases, you will pick them all up and they will show the separation on the phase plots to correspond with the sine waves. It can blur out a little bit more, but normally you can see them quite well. If you do think you have a three-phase or a two-phase issue, getting that phase lock is absolutely critical, because you can imagine if this starts to blur even a small amount, it can start to just look like noise and you'll lose all of that clustering very quickly. So then moving on to the ultrasonic type discharge. Again, we have a number of different patterns and they all follow the same general rules. One of the easiest to distinguish is corona type discharge. Corona type discharge, heard on the ultrasonic sensors, is only ever active on one half of the sine wave. Not only, occasionally at very high voltages, you'll see a very sparse one, but for the predominant amount of your testing, it will be active on one half of the sine wave. It also has a very distinguishable low crackling sound when you are testing on site or listening to the sound recordings. Your surface tracking type discharge will occur as two clusters or humps of data with the 180 degree separation. Very similar to the TEV phase plots. And if you then start to get multiple phases involved, you'll just notice the on period, or how long it's at its peak for, starts to elongate. So you notice that this here is nearly twice as long as these clusters, indicating that it's over two phases. You've then got your gap or contact type discharge again, which once again looks like the long bars of activity. And it's very similar to the TEV results. So we'll move on to some case studies of what we have physically found in the field and have got good data coming back from. So when you are looking at field data, most of the field data I look at, I am physically the person in the field and I do a lot of my analysis in the field and I can do further testing. However, when you are back in an office, depending how your company works, you may be getting data that was recorded by someone else and you're being asked to analyze it. So at that point, one of the best things that you can do is get good recording data sent back to you with what the person has done. All of these recordings, you can write notes in, you can write comments. What I've done a lot is I've written notes and I've taken a picture of those notes and uploaded it into recordings just so I had all of the data that I needed for further analysis when I was back at the office. Because looking at this phase plot, it's really quite simple to look at it and think, I've got two clusters of activity. I've got that perfect leading edge in the waveform that we know is incorporated with internal void PD. I know it's taken on a TEV reading, therefore it's most likely to be internal void PD. And I can see all that, but what I can't tell from this phase plot alone is the location of the defect. And that's something that you need the site data to do. So for this one, we went through a couple of different steps in order to figure out where it was likely coming from. The first was to look up in databases if there are any common manufacturing defects within that switchgear, and it happened that there was within the CTs. We also on site do a lot of time of flight location using the UltraTEV Locator. So this particular one located it to a specific panel and then to the CT chamber as well, is where the signals were the highest. And then we were able to use the time of flight location on the cable coming out of the cable box as well, and it indicated the signals were coming from within the switchgear compared to further down the cables. So from all of that testing on site, we were able to confirm that it's definitely coming from within the switchgear, coming from a very specific panel, and it was the highest when testing on the CT chamber. That, in correlation with the fact there is a known manufacturing defect on the CTs, allowed us to make that call. Another test that we did was we did the ultrasonic testing all over the switchgear, and we found no ultrasonic signals, which means that if you look at the list we put up earlier, if it could be picked up with the ultrasonic signals, it's more likely to be on the outside of the switch of the insulation. Whereas because there were none of those signals, and there were TEV signals, we assumed that it was coming from within solid insulation, and it all lined up, and it ended up coming from within the CTs. And you can actually see a picture of one of them failed here. This is another one of TEV with a very similar scenario, but it's where you start to get a lot more defects within the one space. So once again, we were on site and we found this phase plot you see here, and it was testing on the back of this pitch-filled cable box. So when we did the testing, you see this type of a phase plot, and this is a quite complicated phase plot, because if we analyze it, we can see one set of clusters here at the top, quite high level. I then see another set here and here on a different phase, potentially one here, lining up here, and maybe another one that's not fully developed on the other side. But there are potentially 4 defects in this phase plot across 3 separate phases. And it was found right here in the, on the outside of the cable box around where the cable would trifurcate. We did the time of flight location. Once again, it pinpointed it to come from here, and pointing into the switchgear was the height. What we then did was use the ultrasonic contact probe and placed it right where the cables would trifurcate. And this is one of the few scenarios that actually goes against what I said earlier of you won't find those internal void sources with ultrasonic testing. But when we placed it on the outside, we could hear this particular discharge source buzzing or arcing, sparking. So this was just one of the scenarios where still doing that test was a good option. And what it drew us to conclude is, whilst it is an internal void discharge, probably around the trifurcation where the pitch was poured in, there may have been a crack or a big enough of a void that led to the outside of this metalwork so that we could hear it using that ultrasonic contact probe. So once again, we used all of them together. We knew the nature of pitch and the pouring of pitch in, and were able to conclude where this PD source was most likely coming from. I can't tell exactly where all of the 4 individual sources are within here, but we know that it's strongest right at the cable termination. Moving on to quite an interesting one. So this is when we were testing transformer cables. So the TEV found this source first, leading out, and we were able to once again do the time of flight location to point into the transformer and specifically to the blue phase. When we were doing that, we also then used the UHF, and it was able to confirm it, both signals looking very similar with that cloud-like clustering emanating from the middle, 2 clusters 180 degrees separated. The very interesting part about this is we were also able to put the contact probe on the outside of the metalwork and listen in, and we found that it was actually the tap change discharging. We could audibly hear it as well. So it's a very good scenario of all of the test methods coinciding to find the location. But being able to hear it ultrasonically is quite rare as well. But knowing that there is a TEV type discharge located to the blue phase and within the transformer itself would be enough to do further testing of like DGA testing. So it'd be very important to use that type of method with the TEV location in order to figure out the true source. And that's just the large one of the UHF coming from. So moving away from TEV and focusing on surface discharge. So whereas TEV is looking for those internal voids, we're now looking at the ultrasonic, looking at the surface type discharge. So this one is a very, very easy scenario. So this is an Hazenmeyer RMU, and you can see immediately from looking at it, these cables are too close together and there is discharge happening. So once the screens are taken off and the cables remain too close to one another, you get discharge occurring between the insulation layers. Looking at this phase plot, it's very clear there's two clusters of activity occurring with 180-degree separation. If we do look over at the information, the ultrasonic algorithm has classified this as PD with 100% surety. So this is your easiest example because you can see this the second you open the door, and it's very, very easy. The sound file for this was also a harsh crackling sound, and you can actually hear it with your own naked ear, making it very easy to identify. This one's a little bit more in depth, and it's what you get once you start to have two sources of discharge on separate phases on the same asset. So these are your HV fuses on a quite old RMU, and you can see at the bottom right here this white powder of the discharge occurring between the two insulation layers. Now it was occurring here and also on this fuse over here at the exact same point. So when we pointed the ultrasonic dish at this one, we could actually see these two separate phases of activity occurring. So you've got the first phase here with its corresponding 180-degree separation cluster, and then the second phase is here with its corresponding cluster. Again, looking at the algorithm, it's classified as PD based off the sound file with a 97% surety, which is very high. So looking at that, again, we could do an open inspection and find the problem almost immediately visually. Because it is an ultrasonic type problem, picking up surface tracking, when you do an inspection, you will be able to find it and you will be able to see it. And that's something you should always keep in mind, and why knowing what type of test you've done is really important when you start to look at the maintenance of these problems. This one was also picked up on UHF. So you can see on UHF, we've got two clusters of activity, but interestingly, only one of the sources was picked up. Probably just due to how we were standing. There is a little bit of activity, but not as much. The final one we'll look through is cable PD case studies. Cable PD is quite an interesting one. And this particular source is one I found. And it was when I was doing RMU testing in the streets. So what we did is we went to one RMU and I identified this TEV phase plot here. And again, you can see two clusters. It is forming a little bit of a wave, but it's quite sparse. It's not exactly what I was expecting to see if I was on a local a termination type defect. So we tested, and I did the UltraTEV Locator testing. And this time, rather than pointing into the switchgear, it actually pointed further down the cable. Due to that, I did some HFCT testing and found a very, very similar phase plot as the TEV. And I then found the rise time with the waveforms, which are a different set of analysis. So because it was pointing down, what I did was I went to the other end of the cable. It was about 75 meters away, the next RMU. So I went to that side, and what we found was actually a very similar phase plot. We did the time of flight locating again, and once again it pointed down. So what we had was two RMUs quite close, like a single cable joining them, and both were indicating the problem was between the RMUs. So at that point, we used our cable data collector, and we actually did a bit more in-depth analysis and found that the problem was 75% from one end and 25% down the cable from the other. We were able to then get up the cable drawings, and what we found is there was actually a joint on that cable right outside of one of the RMUs, which lined up perfectly with where our waveforms were telling us the PD was emanating from. So once you start to get cable PD, you do need a bit more information about the switchgear or the cable more specifically. You need to know the cable type and the length of the cable as well in order to get that distance to PD location. But once you do all have that data, you're able to really well narrow it down, pinpoint where it's coming from. And it's really important to take that into consideration, because if you only do the testing, you would have seen these two TEV phase plots, both of which are on both RMUs, And if you didn't do the time of flight or the cable testing, you could have easily mistaken that to be a problem in the terminations and done work that wouldn't have fixed the problem. So the time of flight location was really important in this scenario. And I'll pass back to Brad for a summary.
Good. I've been typing furiously, answering questions. Okay, so that has just about brought us to the end. There's no active. Oh, we'll just have one more.
Well, you've finished the summary.
Yeah, we'll finish this. Okay, so just in summary, data analysis. So data analysis begins when you're in the field and you are running the tests yourself, or the people that are running the tests for you. They're already starting to analyze the PD data, and it can be done very well with this. Okay, so you've got to figure out, how are the signals behaving on site? Am I hearing sound? Am I getting TEV? Can I see it with the HFCT? Can I see it with the UHF? Sometimes certain defects will give you TEV signals and ultrasonic signals, and you can pick it up with every single sensor. Sometimes you'll only get it with one sensor. A very common one is surface PD. Most of the time, surface PD will only give you an ultrasonic signal. The sparks that are occurring don't have enough energy in them to give off electromagnetic energy, so you won't find it with the TEV. You might just find it with the HFCT. You may not find it with the UHF. It depends about the line of sight from your sensors to the activity, and also vice versa to that. If you've got a void on the inside of solid insulation, very, very rare, well, it's pretty much always happens that you won't be able to hear it because the sound can't get out from that sensor. Okay, so are multiple sensors seeing the same activity? That's one of the thought processes you need to do in the field for the reasons that I just explained to you. So we want to understand how a phase resolved partial discharge pattern works. So your knowledge of how did this pattern get created? Where are the signals coming from? What sensor am I using to detect these signals? Are the signals traveling or are they local to me? Look at all my data. That will help you come up with an answer about what is most likely the problem. And then to be able to allow you to do all this analysis, we want to capture the best data possible. Better data equals better decisions. So if we're using this to its full potential, if we're capturing the phase plots correctly, if we're locking onto the phasing when it's time to record the data, if we're using the right sensors, if we're using them in the right way, and we are capturing full records, we're going to be able to make better decisions on the PD activity that we're capturing. It'll also help you diagnose noise. A lot of the signals that we capture are noise, and they're not detrimental to the asset. But you've got to be able to get through the noise to see the real PD, because that's where the problem is, and that's where you need to spend your time and your thinking to figure out what you're going to do about it. Okay, so that is the end of our presentation. With you today has been me, Brad Monaghan, and on my left is Thomas White.
Typing furiously.
We've got a few questions.
We've got a lot come through.
Do you need me to audibly answer some questions?
Yes, ones I'd like you to audibly answer is people finding signals highest on cables on TEV, why that would occur.
Okay, so one of the best spots to test for PD for TEV signals, that is, when you're running a TEV test, just pretend this is a high voltage cable, which it's obviously not, it's my drink bottle, but if this high voltage cable is running into the bottom of an RMU or the bottom of a transformer, if I go up and I run a TEV test on the outside of that cable, the TEV signals that are on that cable are physically only probably a couple of millimeters away from my TEV sensor. So it's all got to do with the distance between your sensor and where the signals are. So if you've got a switchboard here and you've got a cable coming out of the bottom, even if the PD is inside the switchgear, electrically, when you run a test down here on the cable, electrically, it's the best test to run because the sensor is closer.
What they just said, can you stop sharing the screen so they can actually see you?
Okay, how do I do that?
Just go sharing.
Is that sharing?
And just say stop sharing screen, square.
That one?
Yep. And now it's just you.
Now it's just me.
Yep.
Okay, so what I was talking about was running a TEV test on the outside of the cable. If this is the cable, run a TEV test on the outside of it. Physically, the sensor is only probably a couple of millimeters away from the earth screens. And that's where the signals are going to be at their highest amplitude. So the signals can be in the switchgear, and you see it all the time. If you go out and diagnose a real problem in the field, chances are the signals will be lower on the switchgear than they are on the cable. We see it all the time. What's the next one, mate?
Oh, pick one. I've got about 20 to go through.
Oh, we've saved all the questions to last.
Yep.
There you go.
You just did that one. There's a fair few statements come through.
Yeah.
Things like that probably be a answer properly.
Yeah, a couple of them we'll answer offline.
Threshold values.
Threshold values. Is that threshold for what?
Quickly go through what are the common sources of the TEV noise. I'm typing that now.
Okay, so common sources of TEV noise. We can't answer every question right now, but we'll get back to them all anyway. Common sources of TEV noise are electronics. There is also things that chop up the sine wave. So if you've got a variable speed drive, if you've got power supplies that like to chop up the sine wave, that can be a source of noise. You can have nearby mobile phone towers. You can have nearby comms equipment. You can also have a lot of what you find if you've got nearby overhead lines or outdoor yards. A lot of TEV, well, it's not so much noise, but a lot of TEV signals that come to you will be from contact and floating metalwork type issues. That's where you see those rectangular patterns on the screen, or the tight little squares on the screen that look like a big rectangle anyway. And that's where you've got sparks jumping a gap because you've got differences in voltages between different pieces of metal. A lot of that stuff's not detrimental, but it does have a lot of energy in those sparks, and those signals get broadcast a long way. So they're common TEV signals.
Yeah.
That's good.
Discharge. No, that's fine. That one wants to look at properly. Threshold values. What sort of waveform? Show we can send after.
Yeah.
You just did that. I'll see webcam. Can we use the TEV tester during a short circuit test on a transformer unit doing repair at a shop?
Oh, that's a good question. Short circuit test on a transformer. So I think a short circuit test would be very short-lived. Is that where you short out your phases and then liven it up and basically fail the asset? Is that what a short circuit test is? I'm pretty sure that's what it is. Yeah, I think a short, if that's correct me if I'm wrong, but a short circuit test, you short out the phases and then liven it up and fail the asset. For that, what would technically happen is you would probably get a massive pulse of electromagnetic energy that you can pick up via the TEV, and you'll probably get a massive pulse of sound that you can pick up via your ultrasonic dish. It would be very short-lived, and you may not be able to get a good recording of it because it happens so quick. Your volts are on, the power's on, and then the volts are off. So it's probably not the best application of the instrument. Where it can get used in a workshop type scenario is if you high pot something, trying to figure out if there's PD in there, and you can run the tests, run a TEV test, run an ultrasonic test. You can figure out if there's any internal void issues, or you can figure out whether you've got any surface PD issues. One of the really good ways to use the ultrasonic dish when you are high potting things is to figure out if your test setup is noisy in the first place, because you can point this at your test setup, all the connections from your high pot set to the asset under test, and you can figure out if there's any noise coming from those spots. You might have corona, you might have a gap type issue, you might have some surface PD. But short circuiting tests, I would say no, because the test doesn't last very long.
There are a couple here which we will answer a bit more formally. They're going into quite nitty-gritty little things, and we'll get through them. You'll receive an email with all the answers. Yep. But one that's just come through is, can the UltraTEV tester be used in conjunction with a thermal camera scan? And that is something that both Brad and myself do. It's I'd say most useful in your outdoor yards where you can actually see the assets and they're exposed. But we have found if you have got say an ABS that's hot, then you do get ultrasonic discharge coming with it. It doesn't always fully correlate, but it is something that we do.
Yeah. The thing with, will PD discharges give you thermal activity? And the answer is sometimes, and the answer is it depends. So if PD is fairly far advanced and it's got a lot of energy in the sparks, you've got a good chance that it will give you PD. I mean, give you a thermal signature. But a lot of the time, the heat won't be high enough to give you an answer. And people will have case studies of that all over the world. So they can be used in conjunction with each other, but whenever you've got PD, it's not always going to give you a thermal signature. And also vice versa. Whenever you've got a thermal signature, it won't always give you PD signals because you may not have sparks jumping a gap. It's just the way it is.
One that I was just typing, but I'll answer, is on the phase plots. Someone was just wondering how the density of it actually works. So the different colors you see on the phase plot represent the density. So over that 10-second sample, there is a chance that the same amplitude at the same point in the sine wave will be hit multiple times. So it just builds up a density plot, and that's what you're seeing with the different colors. It traditionally goes from green to blue to red, but the specifics of it and the numbers do change on each plot depending on how much activity you have. But it is on every plot there is a legend. It's just the ones and the quality of the video presentation makes it a bit hard to see. But you can see them in all of the proper recordings. It's very clear.
Yeah. Overall, the pattern is the most important. The density is just how often it's happening. Yeah. It is the main thing. Like if we showed you every phase plot here in black and white today, that question wouldn't have come up and we'd still be analysing the data the exact same way. It's showing you a heat map. Yeah, like what Tom said. Just any other?
Oh, we've got a lot.
We've got a lot of questions.
I'm just going through.
All right, we'll take one more. We'll take one more question and then we'll wrap it up. We'll get back to everyone anyway.
Yeah, we will. I'll just do a very quick one. Then we'll do it. All of these can export in CSV data. All of the program comes with it. You don't actually need any software to get all the data out of the +2, and it can export everything into CSV. So you can have the data and you can play with it. That's just a quick one. And do you want to pick the final one?
Oh, last one.
Yeah.
One more. We got
forms.
Okay, so we've got a question. How do you use the histogram and the frequency plot in analysis? So truth is, I don't use the histogram pretty much at all. I use it a little bit. What it does, the histogram counts up how many pulses occurred within that decibel range. But when I look at the phase plot, 95% of my analysis is already done just by looking at the pattern within the phase plot. So sometimes I'll go back to the histogram if I want to see what a lower level source, just say you've got two sources on a phase plot. So just say you've got a big source, two big waves come up, and then you've got two little ones coming up down below. If you wanted to figure out what the pulse per cycle count was of that smaller one, you could go back, look at where the dots lined up, or the events I should say, lined up in the phase plot with the decibel levels, and you can figure out a pulse per cycle count for that. But I don't use it all that much. Sorry to just, but that's just, I don't use it.
I think we might have to leave it there because I've got about 20 more questions to go through, but we will sit and we will answer all of the questions and we will send them out to everyone. It's just we could be here all day doing question time. But everyone will get a copy of all of the questions and all of our corresponding answers. And if you do have any further questions you can reply to the emails and we will get you all the details that you need. So other than that, thank you for your time. Thank you for coming and listening to us talk about it. If you do have any very specific details, if you would like more information about anything, both Brad and my details have been there. Feel free to send us an email, contact us on LinkedIn, and we can get you anything that you need.
All right, thanks for coming along, and we'll run a third one at a date we haven't set yet, but the last of the 3 webinars. Yep. And that's about what to do once you've found all the PD. What are the next steps you can take? That type of thing. So, yeah.
Thank you very much.
Stay safe.